Questions so far? No? Okay, that's good. So, during the last lecture, we talked about fan of flow and Rayleigh flow, and the idea was applying heat transfer to a constant area duct, or considering the friction in a constant area duct actually acts the same as changing the area of the duct, right? So we can have choking conditions the same as a variable area duct when you have the friction, when you consider the friction, or when you apply some sort of a heat flux to your duct, right? So we talked about the equations, the main equations for we covered all the Rayleigh flow. We talked a little bit about the Fano flow. Again, Fano flow is the adiabatic flow of a calorically perfect gas in a constant area duct with friction, right? So we had the equations, momentum equation, the conservation of mass equation here first, right? Momentum equation, the difference between the two, the Rayleigh flow and this flow, as far as the momentum equation goes, was the friction term. So you have an additional force that is acting on your flow, which means that which will result in the fluid impulse being different at the inlet and the outlet. So we won't have any conservation of the fluid impulse, right? And we will talk about the fluid impulse a little bit further in the lecture. And we also have the energy equation, which was the other difference between Fano flow and the Rayleigh flow. Okay. So we saw this, and eventually we massaged the equations a little bit to come to this final equation. Now for the online people, I always have to keep in mind that I am recording this lecture as well. And don't see the cursor. I'm talking about this equation. This equation. It's hard to do it with mouse, right? So we are essentially relating the friction coefficient and the length or the location in the duct we are working on, which is identified by dx, right? To the changes in temperature and changes in and the Mach number, and the Mach number of that specific location. Okay. Okay. So the goal here, I think we talked about these parts. That's why we want to go into that one detail. But the goal here is to find a relationship between the Mach number, the local Mach number, and the friction coefficient, to reduce the variables. Either have a relationship with temperature or the Mach number or pressure, or just one relation, just one independent variable. And we already have the dependent variable, which is your friction coefficient, essentially. So to do so, we have to find a relationship between changes in temperature and changes in Mach number, so dm over m and dt over t, right? And we already have the relationship between the total temperature and temperature, the ratio over there. We can play with that a little bit, plug that in, use the logarithmic derivative, right? To find the relationship between dt over t and dm over n. Plug that in, you get to this equation, and eventually we'll end up with this main equation here, right? Which relates your friction coefficient to the length, to the local point inside the duct, and the Mach number and at that specific location, and the changes in the Mach number. Keep in mind for the friction for the fan-off flow, we derive the equation for a very small element inside the dot, right? So that's why we have the derivatives, dm and dx, right? So to be able to apply that equation, before going forward, I don't know. Let's talk about the relationship between the changes in Mach number and the friction coefficient, between the left-hand side and the right-hand side of the equation, right? We know at this point, we already know that there is choking happening in the fan flow, right? But we want to investigate it mathematically, right? Why does it happen? So let's look at this left-hand side of the equation. What is the sign of this part of the equation? It is going to always be positive, right? Because 4 is a positive value, friction coefficient is always positive, either 0 or positive, right? But we are talking about the friction flow, fan flow. So it is always positive. dx is a length scale, right? Length is always positive. And the hydraulic diameter is also always positive. So this part of the flow is always positive, right? Let's look at this part of the flow. Mach number is always positive. Here also this term is always positive. Yeah, let me use the cursor because of the online people. Where is the cursor? So this term is always positive, right? And for air, specifically we are dealing with air or any kind of gas, gamma is 1.4 or larger than 1. So the second term on the denominator is also always positive. But what can we say about the term on the numerator? Is this always positive?
Only if the Mach number is less than 1.
If the Mach number is less than 1, this term is also always positive. But if the Mach number is larger than 1, then this term is going to be always negative. So what does that mean for the dm squared? Because the left-hand side is always going to be positive, right? So the right-hand side must always be positive as well, right? So what this means is that if your Mach number is smaller than 1, right, the numerator term is always positive, and the changes in Mach number has to always be positive as well. So dm must be always positive, right? Which means that when you at your inlet, when you have a subsonic flow, your Mach number will increase, okay, until it reaches the sonic conditions or Mach 1. Or what will happen when you are dealing with the supersonic flow, right? Numerator here is going to be always negative, so this dm must be negative as well for the equation to hold true. So this negative dm means that your Mach number is decreasing, right? If you are in a supersonic flow. So if your inlet is supersonic, you will have the Mach number will decrease, and you will get to the sonic condition. That actually this explains the choking of a Fano flow mathematically. We could have done the same for the Rayleigh flow, but did we check the choking in the Rayleigh flow mathematically or not? I don't recall. I don't think we did. But it is essentially the same thing. We had an equation that related the heat flux to the Mach number and the changes in Mach number, right? One side of the equation was always positive, and you should have made the same conclusion for the other side. So if you go back and check the equation, I'm pretty sure you'll get there. So yeah, it is similar to the Rayleigh flow, where heating causes the flow to approach a choking condition. And in both cases, friction and heating essentially act like a valve, or in effect, a flow area reduction. Okay? So what we want to do, essentially, the conclusion from this equation is that with a supersonic or subsonic flow, you will eventually, the maximum you can get is a sonic condition, right? Does it make sense? At the outlet, right? or the maximum or the minimum, depending on whether the flow is subsonic or the supersonic. So to find the final equation, which is going to be an integration of this equation we have here, we have to integrate from your inlet Mach number to the sonic condition, which is the Mach number 1 for the dn. And for the dx, it's going to be from 0, location 0, to the length of the exit length of the duct. Does that make sense? Okay. So let's take that integral, and we call that exit length. Since we are dealing with the sonic condition, we are dealing with the star condition, so that exit length at the sonic condition is going to be called L star. Okay, so if you take that integral, the left hand side is pretty simple. It's just going to be 4 multiplied by CL or multiplied by L star over the hydraulic diameter. The right hand side is a little complicated, and you will get this long equation that has some like natural log terms in it, and we have the ratios of the Mach numbers. Keep in mind that this Mach number here is your inlet Mach number, right? Because the outlet Mach number is 1, is the sonic condition, right? So this integration is done from inlet to the sonic condition. That sonic condition can be the outlet, can be like larger than the outlet, like can be inside the duct. Any questions so far? Okay. So we can find all the relationships for the sonic condition, all the ratios for the sonic condition as well as we did for the Rayleigh flow, and also the variable area. The temperature ratio is going to be equal to this. We already have these ratios. We can just reuse them, right? The density ratio is going to be can be calculated using this equation, and the pressure ratio can be calculated using this equation. Is there any questions so far? So here, before moving on, I want to give you a bonus point, and I assume you may guess what is the bonus point. Take this integral, is that right? Essentially what I mean is take this integral, take the integral of this equation, this equation right here, and get to this equation. Okay? And if you do so, you'll get 1 bonus point, which is equal to half a point in your final grade out of 100. You always have to keep in mind that you're taking the integral with respect to dn squared, not dn. Right, so your independent variable here is m squared, which is going to make everything a little bit easier. Okay, so we can find the fluid impulse, the ratio between the fluid impulse at the inlet and the star condition as well, based on the definition of fluid impulse. And also we can have the changes in total pressure or stagnation pressure. Is there any questions so far? Okay. So as we did for the Rayleigh flow, what we want to do is to be able to plot the TS diagram, right? And this diagram on the left is essentially we are plotting the evolution of the ratio, right? For sonic and subsonic and supersonic condition. For example, if you want to go if you want to look at it a little further, like your pressure ratio P to the sonic condition, of course at Mach number, as Mach 1 in the inlet, your ratio is going to be 1, right? So that's why all of them essentially intersect here, except for the friction coefficient, which is going to be going to 0, essentially, right? And just evolution of the ratios. So there's nothing special about this plot. But the plot that we really care about is going to be the TS diagram, right? We are going to use the Gibbs equation again, the famous Gibbs equation, and the same as the Rayleigh flow, we can play with that Gibbs equation and come up with the changes of entropy with respect to changes in temperature. So the TS diagram. So we can plot. We will be able to plot the TS diagram. If you plot the TS diagram, you will get something like this. So essentially, in a subsonic branch of the flow, your temperature, as you go with in a friction, in a fan flow, when you have friction, when you have involved friction, we are moving towards the sonic condition, M1, right? Which means that subsonic flow, you start from a mark that is smaller than 1, you go towards 1, and your temperature actually decreases, right? In a fan flow. When you start from a subsonic inlet, right? When your inlet is a subsonic condition. As your entropy increases, your temperature decreases. And we can have the supersonic conditions as well. Supersonic inlet, when you start with a 0.1 supersonic inlet, your Mach number decreases to the sonic condition with an increase in temperature. Is there any questions? And you get to a maximum entropy value at the sonic condition. Can we find this maximum entropy value? Yes? No? Yes. Okay. Obviously. How can we find it?
Integrate that equation.
Do we need to integrate that equation though? So the maximum happens when you eventually have to integrate it. You're right. But so my question is, where does that maximum happen? At n equals to 1, where ds over dt is 0. So you can simply prove that maximum happened at n equals to 1, right? So if you move the dt to this side, ds over dt must be 0. And in order for the left-hand side to be 0, right-hand side must be 0 as well, which means that n must be equals to 1. That doesn't really make it good. But yeah, you essentially can integrate, you should integrate that equation to be able to find the maximum entropy. And this phenomena in a fan of flow, the phenomena of choking, is called the frictional choking. So this is actually very important in propulsion. And we'll get to talk a little bit about this when we are talking about the fluid impulse. Okay. But let's compare this and also the Rayleigh flow to the normal shock. Okay. Let's say you are at your inlet, you have a supersonic flow coming in a duct, inside the duct, right? And your duct is long enough for the choking to happen. Okay? Or your duct, let's say we are in a Rayleigh flow, we are applying heat transfer. Your heat transfer, amount of heat transfer you're applying is high enough to see the choking, right? So what's going to happen inside inside the duct when you're approaching when your inlet is at the supersonic condition? What's going to happen inside the duct? You are going to have a normal shock wave, right? That's a pretty important conclusion, because what it means is that you can actually you can replace in your analysis, if you will, or to put it in better terms, you can say that normal shock wave is pretty similar to Fano flow and Rayleigh flow, both of them, right? And you can actually use the TS diagram for the Fano flow. This one is the Rayleigh line, right? This one is the Fano one, right? You can use this TS diagram to calculate the shock properties for a specific type of flow. Shock properties before and after a shock, downstream and upstream shock. Okay? How can you do that? It's pretty simple. So if you have the TS diagram for a specific type of flow, for Rayleigh and Fano conditions, right? For a specific type of gas, the intersecting parts of the flow, where is this? Yeah. This part 1 and part 2, are essentially downstream and upstream and normal shock wave. Does it make sense?
So the first intersection, that's upstream, the normal shock.
Yes, exactly. Because these parts represented the supersonic conditions, right? Yeah. And if you wanted to say, so essentially in a Rayleigh flow, the conservation of mass equation and the momentum equation is exactly the same for the normal shock, for the shock wave, and the Rayleigh flow. The only equation that is different is the energy equation, which accounts for your heat transfer. And for a Fano flow, conservation of mass equation and the energy equation are exactly the same for the shock wave and the Fano flow, right? Okay, so let's move on. Again, we talked about this, I think. We definitely talked about this when we were talking about Rayleigh flow. But essentially the same phenomena happens for the Fano flow. When you have a subsonic flow coming in at the inlet, and your length of the duct is larger than the sonic length. And what was the sonic length? Sonic length was the length at which you will get the sonic condition, the choking condition. So if the length of the duct is larger than the sonic length, then the flow will make some adjustment, so your inlet, your outlet will be the new sonic condition, the new choking length. Does that make sense? Okay? Which means that we are going to have some sort of escalation around the duct or some sort of backflow, depending on the condition, right? If you are approaching it with a subsonic flow, right? But when you are approaching your duct with a supersonic flow and your length is larger than the sonic length, the adjustment of the flow is made by normal shock wave. So the main conclusion you should make here is this, for both Fano flows and the Rayleigh flows. If you are approaching the flow with either a subsonic or a supersonic flow, right? And your length is larger than the sonic length, the flow will make some adjustment depending on whether it is subsonic or supersonic, it's going to be different. But it will make some adjustment nonetheless, so that your outlet condition is going to be definitely the sonic condition, right? Again, if your length is larger than the sonic length, adjustment will be made so the outlet is going to be the sonic condition. Okay? Is there any questions here?
So is that kind of similar to like a nozzle, like a supersonic nozzle that after the shock, then it'll be like subsonic, so then the flow will increase again?
Exactly. And we will talk about that actually right away. So before moving on, there was something that I forgot to mention at the beginning of the class. Your first quiz will be posted next Friday, okay? And it will cover only chapter 1 and 2. Hopefully by next Friday we have definitely started chapter 3. I'm hoping we have definitely started chapter 3. Okay? Today we will definitely finish chapter 2. And one other important announcement. I'm pretty sure you have seen the university calendar, but because of this COVID situation, there is no real holidays anymore, right? So the Labor Day, there is no face-to-face classes, but I will post an online lecture. And that online lecture, what I'm going to do is I'm going to solve a lot of examples from chapter 2, right? Some of them will be the examples that are already solved in the book. Some of them will be the problems that are at the end of each chapter. And I have to go back to the syllabus and see when I should post the homework, but it is around this time. Sometime next week that I will post the homework, right?
Would that be like one of the weighted quizzes or one of like the attendance quizzes?
That will be one of the... I have to go back to the syllabus, so the quiz, those midterm quizzes, midterm replacement quizzes have a set date, right? So I have to go back to the syllabus and check the date. If next Friday you're supposed to have one of those weighted quizzes, you will, that it will be considered in your final grade, right? I will give you 1 hour to solve basically 2 problems. And for those of you who have had a class with me, you know that most of the problems I give in a quiz or exam are from the book problems, right? So not outside of the book. So if you can solve the book problems, you should be all right. But don't cheat, right? Don't go and find the solutions. I don't think you can find the solutions to I don't know. I don't think you can find the solutions to the problems of this book. But if I feel like you are cheating, I will definitely design the problems myself. It's going to be harder.
And the homework is going to be book problems, right?
Yes. Any questions about the quizzes or the exams? No?
Do we have a lab quiz this week for lab 2?
Lab 2. Is there a quiz on the syllabus? If there is, then I will post the quiz, yeah. I don't know, I have to double check the syllabus, right? If there is one listed on the syllabus, you will get a lab quiz. I think I said it in the lecture, though.
Well, I think you said there's one next week for Euler buckling. I don't know if you said anything about that.
So there will be one next week, then, for the Euler buckling, yeah. Is there any questions about the Fano flow, Rayleigh flow, or anything else? No. So let's do this. We are going to try to essentially come up with a solution procedure for this type of flows, Fano flow and the Rayleigh flow. I mean, the focus is going to be on the Fano flow, but you can essentially apply the same procedure or the same ideas to the Rayleigh flow solutions as well. Okay? And the goal here in these type of problems is to establish the exit flow conditions, right? So what should we do? I want to write on this tablet, laptop. This is going to be hard. So the first, there are going to be three main conditions, right? Let's say we have a duct. We don't have any heat transfer. Area is constant. We only have wall friction, right? We have an inlet condition. We know the inlet condition. We want to find what are the exit flow properties, right? So based on what we said, since we have friction, we may experience choking. So the first thing you want to do is to check whether you will experience choking or not, right? That's the first thing you want to do. Check. Sorry for my bad handwriting. I'm writing on a laptop essentially. Okay, so we want to check the choking conditions first. First of all, before this, you definitely have to calculate the hydraulic diameter. I'm going to ask again, what is the equation for hydraulic diameter calculations?
4 times the area divided by the circumference.
Exactly. So 4 times area divided by the circumference. So that if it's a circular duct, it means that the real diameter is going to be your hydraulic diameter. If it's a square duct or a rectangular duct, it is going to be different, right? So you have to make the calculation. So calculate the hydraulic diameter first, and we want to check the choking conditions. How many situations can we have as far as the choking conditions goes? So to check the choking conditions, you have to find L star, right? How can we find L star? How can you find L star?
Use the equation that relates dx and n.
Exactly. Use this equation here. Use the first equation on the board here, right? This part has the L star, and this part is the other side of the equation. Again, this M here in this equation is your inlet Mach number. Okay. So by using this, you can find L star. And what was L star again? L star was the choking length, right? And then you compare this L star with the real length of the duct. Okay. How many situations can we have there? It's pretty simple, right? Either your length is larger than the L star, or it is equal to this L star, or it is smaller than the L star, right? Let's start with a smaller one. Let's say your length is smaller than the L star. So what does this mean?
You won't reach the choking condition.
You won't reach the choking condition. Exactly. So the choking condition will not happen. I'm going to write this down, but choking not happening. You get the idea. So how can we find the exit conditions, the outlet conditions here? Let's actually try to see if if we can have a brainstorming on this.
If there's no choking, that shouldn't affect the flow.
It will not affect the flow, but all of the relationships we have relates the inlet and the choking and the sonic conditions, right? So we don't have any equation that relates the inlet to the outlet regularly, right? So we just have to like play with the concepts and the equations we have a little bit to find a solution to this, right? So let's start from here, Lorianne, right?
Yes, sir.
So let's start from here. Let's like chime in, whatever idea you have. So all of the equations we have relate the inlet condition to the sonic condition, to the choking condition, right? And here we are saying that your length is smaller than the choking length, right? And we want to find the exit condition, like pressures, whatever, right? What do you think you should do? If you don't have any idea, that's all right. Okay, Ryan?
Should we somehow use like the graph for fan outflow before we reach the choking condition and find like entropy or something like that?
Use the graph and find the entropy. But do you know what is the Mach number? The graph had the Mach number on it, right? Do you know what is the Mach number at the inlet? You don't, right? So let's go to Nila has already chimed in. You're of course welcome to say
I
add
think
to
if
what.
there's going to be no choking, if you enter in a sonic condition, you'll exit out of sonic condition.
Can you repeat that?
I said if there's no choking happening, then if you enter in, say, at a sonic condition, you'd exit with a sonic condition. Assuming there's no, in a sonic condition, there's no backflow happening either, right? There's nothing.
Yeah, it's just a regular flow.
Yeah, so
Regular
if it
flow
goes-
with friction.
If it goes straight through the length of the tube, then at the end of it, it should be sonic as well.
No. So let's say we are starting with a subsonic condition and smaller than 1, and what we are saying is that the length is smaller than the sonic length. So you could have gotten to m equals to 1 here, right? But at this point, you have a Mach number that is larger than your inlet, but it is not. It is smaller than the sonic condition.
So, is it like the average then?
It is not the average, no. It doesn't change linearly, but I really like that idea. Like you could have done a weighted average, and it could give you a good estimation, right? But it is not the average.
Could you interpolate it?
No, it's still not, because you cannot assume it is a linear change, right?
I don't know how idea.
Okay. Tyler?
Could you consider like what stays the same for the inlet and outlet, and then use some of the like momentum conservation or one of those fundamental equations?
It is going to be pretty tough though. I mean, you can definitely go back to the main governing equations. That you always can do that, but we don't want to do it. We want to make it easier, right?
Well, if that's, can we safely say that there is no choking because?
Yeah, sure, definitely.
Not no choking, well, can we say that that isn't a change in area, essentially, because?
That's the assumption. Yeah, the area doesn't change at all.
Right.
It is a constant area duct, right?
Well, I mean, like, changing area because of adding heat or friction.
We are saying that. So what we are saying is a metaphorical change in area, right?
Yeah.
We are saying that there is a metaphorical change in area, right? Because of friction. So we don't want to say that it's not. We are saying that there is. So yeah, I guess you wanted to get to the Bernoulli equation then, right?
Something like that.
No, you cannot use the Bernoulli equation.
Okay.
So, Anna Victoria, are you done, Samir?
Yeah.
Okay.
I'm not sure, do we know anything about the pressure and temperature at the
We know the inlet conditions, yeah.
Because I know that in the beginning, before we went to the final flow, we were eliminating, well, I guess because we had heat transfer and stuff, we were eliminating like the temperature at the inlet, the temperature at the outlet. Can we use those equations that we have, like the ratios of pressure, temperature?
So you're either talking about the relationships we derived for the shock waves or the area, the changing area relationship, right? Because those were the only ones. And over there, we were not including the frictional losses, right? So those ratios don't work as well.
Josh, you will.
He has been asleep all the class, so.
I would say maybe we use like conservation of momentum or something similar to that.
We can definitely do conservation of momentum, but I don't know if we want to, because then it will be much harder. Okay. I didn't expect you to answer this, but I just want to make sure all of you are awake. Let's see what we can do. So what we are saying is that the choking condition will not be reached, right? Okay. Can we, and we have the length, right? We have the length we have the L star and we have the length of the duct. Let's say we subtract these two lengths, right? L minus L star. What are we going to have? We are going to have the distance from the outlet to the choking condition. Okay? Can we assume in our mind that this outlet is the inlet of another duct for which outlet is the choking condition? Right? So based on that, you can very simply, use the ratios just by subtracting this length. Use the ratios we already have to find the Mach number at the new inlet, which is the outlet for the other one, right, for the previous case, and all the other parameters. Does it make sense? Is this clear? You see, so it is a pretty simple solution. It may be a little hard to conceptualize though, right? So essentially we are,
Basically you're working backwards, so you know that the exit is Mach 1, so, and you have the difference in the length, so all you're doing is fine.
Exactly, that's right. So all you're doing, so what you do after calculating the hydraulic diameter, after calculating the L star, you use the ratios you have and real inlet conditions to find the properties and the choking length, right? Like P star, whatever, right? And you use these properties and the choking length, right, to find the new inlet properties. Does this make sense? I just want to make sure that all of you are clear on this. Yes? Clear? Okay. Yeah, it is a pretty easy solution, and I mean you definitely have seen a lot of these type of solutions, but sometimes it gets a little confusing. Okay, so the second case is going to be where your length is going to be equal to L star, right? So how can we find the exit conditions for this case?
They're equal.
Essentially, you find the exit condition for the choking. You find the choking conditions, and that's it, right? You already have the relationships and everything else. Okay. But the hardest condition is actually where your length is larger than the LS star. Meaning that the choking happens somewhere inside the duct. Okay? How should we deal with this? Yes.
Sorry, you can go ahead.
Go ahead. No, I just want to say that I want to go around the room again and see if you guys have any ideas.
Maybe it's really silly, but can't we use the same idea that we used before? Just giving the duct in two separate, like taking out one large duct into two separate ducts. Maybe like cut it at the sonic emission, which you know all the parameters.
So what you are saying is that we essentially going to use the same idea, right? This time we know that at some point we are going to get m equals to 1 inside the duct, right? But what's going to happen afterwards? What should we do afterwards? Because so let me ask you this. Let's say you have the choking, right? Choking happens, so what is going to change? Are we going to see, what are we going to see after this? That's my question. After m equals to 1.
I think it's gonna remain the same. It already choked, right? M equals 1, so there's nothing interfering with it anymore.
So you are like 50% correct. At the exit, we are going to have m equals to 1. But it doesn't mean that in this part, m is always 1, right? The idea was the flow will adjust itself, so the exit is going to be the new LS star, the new choking length. Does that make sense, right? So
You have spillage and then
you will have the spillage, right? So when we tell you that, let's say when I tell you that we have this pressure, this Mach number going in, if we are in this, so it is very important to understand that for this specific case, for L larger than N star, we have to separate the solution for subsonic and supersonic, right? And we are going to deal with the subsonic first. Okay.
So what are the adjustments that will be made?
The adjustment that the flow makes is going to be the spillage, right? So the inlet temperature and inlet pressure is going to change, right? The flow goes in a real world solution. The flow goes in, it will be choking, and then what's going to happen? It will be literal choking. Flow cannot move anymore until the pressure changes, right? And then it will move, and then the new inlet conditions will cause the outlet Mach number to be 1, right?
So at the inlet, since it's a supersonic condition, at the
Subsonic. We are talking about
inlet
subsonic.
is subsonic. Okay.
Yeah. And at this point, we are going to first talk about subsonic.
Then there will be backflow and spillage, right?
We will have a spillage or backflow. Yeah, exactly. Right? So what does it mean for pressure and temperature? It is going to mean that your pressure and temperature will increase, right? So essentially, when you have this type of, when you have subsonic flow approaching a duct, which has a length higher than the LS star, than the choking length, what is going to happen is that your pressure and temperature will change so that your outlet is going to be the new LS star. Does that make sense? Okay, so but how can we find the new conditions, right? Essentially what you do is that you find, based on that pressure and temperature, you find the star conditions, right, first, right? LS star conditions.
Can you say based on that?
The old one, the old temperatures. So based on the given data, right? So yeah, always keep in mind that your flow approaches the inlet with the pressure and temperature, and then the pressure and temperature changes, right? So we have an old inlet and the new inlet, right? Okay, so you find the star parameters, right? You find it. You have already found the L star. It is beyond the point. We don't really care about that. But you find based on the old pressures, you find the P star, T star, whatever, right? And then this part is actually the part that may be a little confusing. And then you assume, and this is going to be happening in real world, right? You assume that your L star is going to be changing, right? So your exit length, your duct length is going to be the new L star, okay? And you find a new inlet parameter for that type of duct. Does this make sense? Yeah? So you have an old L star, you assume the new L star is essentially the L, and based on the ratio, and you have already found the P star, whatever, right?
So that is if there's another duct connected to the end of that.
End of what? No.
So you said there's at the outlet, there's a new L star. Is that what you said?
Yes, it is. So let me actually, I have to use the board. It is hard to do this now. So let's have the condition. Condition is your length is larger than the L star. And you know how to calculate L star for an incoming flow. M1, P1, T1, rho 1, whatever. Okay. So your L star is going to be this length, right? What does this mean? It means that you will get some spillage or backflow or whatever. So that your exit condition, at your exit you will get M equals to 1. So eventually, what it means that your pressure and temperature and the Mach number will change, will not remain these values anymore, right? But what we want to do is to find the inlet pressure, inlet temperature. We already know the outlet conditions. It is going to be the star conditions, right? And the star pressure and temperature doesn't really change, right? As long as your Mach is 1, your P is the P star, right? So to find these new inlet parameters, what you do is you already have that calculated the L star based on the old one. You calculate the P star, P star, T star, and rho star, right? And again, the star conditions doesn't change, doesn't really matter what is your L star, right? L star is determined by the inlet, not the sonic condition itself. So the sonic pressure, sonic temperature, all of these are going to remain the same. So you can say that after the adjustments are made, your outlet conditions are these. Does this make sense?
Yeah.
Okay. And then using these parameters and the equations you have, and using this length as the new L star, and the reason we are calling it the new L star is because the Mach number has changed in a way that the L star has changed, the inlet Mach number. Does this make sense? Because of those adjustments. So using this new L star and the ratios you have, you find the, let's call it P1 prime, T1 prime, rho 1 prime, and M1 prime. Is it clear now?
Yeah.
Okay. We'll definitely solve an example from this. So you will see that in an example. And you can always ask any questions you may have outside of the class as well. What time is it? Okay. So, but this was for the subsonic condition, right? What will happen if we are dealing with a supersonic condition? So we just talked about the subsonic. What is the solution when your inlet, before the adjustments are made, is at the supersonic condition? So we said for the supersonic inlet, you are not going to have any spillage or backflow. So your pressure and temperature at the inlet will not change, right? What's going to happen is you are going to get a normal shock inside the duct, all right, in a way that your outlet condition is still the star condition, the sonic condition, right? So the adjustment is made with a normal shock. Okay, so how can we deal with this? Any ideas?
So, we're still assuming those parameters, L is greater than L star?
Yes, yes.
So it's gonna enter in with no backflow and spillage, and it's gonna hit a choking point, and it's gonna go down equals 1 at the outlet.
Yes. We will have a normal shock, and so the adjustment will be through shock, not this. There's no spillage or backflow when you're dealing with supersonic flow.
But we don't know the location of the shock.
We don't know the location of it. That is the hardest part. You don't know where the shock happens, right? So what you want to do is that you want to assume a location for the shock. Okay? Let's call this length. I want to follow your book's nomenclature. Let's call this length L of X, right? So we are assuming at a location this shock happens. At that location, let's say your duct is 1 meter, I'm going to assume that this shock happens at 0.7 meters, okay?
So this is going to be similar to the things you're doing with heat transfer, like with all the guessing and stuff. So
Yeah. That's pretty similar to
So
it.
you just guess the shock and then get the pressures and see if those pressures will eventually get to a Mach at that distance, Mach 1.
Not exactly. You're pretty close actually. Yeah. You are pretty close. But that's actually, can you elaborate a little more? You may be on the right track.
So I was like doing reading over the summer about like the supersonic wind tunnels and stuff, and it's like you kind of just guess and then you use the exit conditions you get using like the upstream Mach or whatever, and then you have final pressure values, and then that has to equalize by like the end of the duct, and then if it's close or not, you like move the shock back or not or forward to get like those equalizing conditions. It's like trial and error basically.
In placing the shock,
Well, because if you know like the upstream conditions, you can get the conditions behind the shock.
so
And
what is the upstream condition here?
well, don't you know like
So the shock is somewhere in between Lx and Ly, right?
Shock. So we are assuming a location for shock, which is this distance Lx from the inlet, right? So this Lx is an assumption we are making, right?
So, making an assumption on Lx.
Yes. And we'll get to a trial and error later on. But something that we know by, we are certain about is the exit conditions, right? What are the exit conditions? The sonic conditions. So this y, Ly, is actually your Ly stop. I think this is where you were getting at, right? Okay. So, any other ideas?
Is there any way you could use integration from the lengths from Lx to Ly?
Integrate what?
You know dm for Ly, Mach is going to be 1.
That's right.
So integrate dm from Lx to Ly.
Integrate dm from Lx to Ly. So from here to here, to find what are we trying to find here?
Well,
the thing is, we already know that this is an inlet after this shock, and we have the sonic conditions here. So using the ratios, whatever we already have, we should be able to find this value, Ly stop, right? Right? Okay. And you can actually, based on that, since we have the length, we should be able to find Lx.
Oh, so wait, so if you know, like you said this, if you know Ly, you can get the conditions right behind the shock, and then you can.
Right after the shock, right?
Well, yeah, right after the shock, and then you can get the upstream Mach right before the shock.
Using the shock properties, right? Exactly. So you can get upstream Mach right before the shock, and you essentially have an Lx and Ly star, right? Okay, so what is next? Let's go again. Let's start from Lorianne and see if we have anything to if she has anything to add. No. Okay. Let's go with Tyler. It is a little confusing, so that's why I'm like emphasizing on it a little more. Because if you go this way that we just described completely, we have assumed the position for the shock, and that's it, right? We don't know whether the positioning is wrong or right. We don't have any way of checking that, right? So the alternative solution doesn't really come into play. Okay? Does it make sense? Okay. So let's say instead of guessing this position, we guess a Mach number behind the shock, right? We know it is happening at an Lx. We just say the Mach number behind the shock is going to be, let's say you start with 2, the Mach number is going to be 1.3, right, before the shock. That is going to be happening at a Lx, at an Lx. We don't know what Lx is. We want to find it out. So going the other way around, right? What's going to happen here? You have an upstream Mach number, right, that you have guessed, right? Then you can, based on the shock properties, you have a downstream Mach number, which is subsonic, right? And then you know that your exit condition is going to be sonic, right? So you can find this L stop. You have the Mach number, you know the exit condition, you can find the L stop. Does it make sense? Right. Ly stop, whatever. Right. So based on that, you can actually can we also find Lx? So we are able to calculate Ly stop, but can we find Lx? We don't want to use L here, right? In the length we know, because we are going off of an assumption, right? We have the Mach number coming in, we have an exit Mach number as well for supersonic flow. So this is a case of case 1, right? Where your L was smaller than the L star. Does this make sense? Are we all following? Right? So you go back to case 1, you calculate the length. I see a little confusion.
Sorry, I started thinking, I'm sorry, I still don't understand the L1. Sorry. I understand what you're saying after,
Okay.
but how do we find the L1?
Okay, so let's just start from the beginning, right? The first thing you do, maybe I shouldn't have started with the wrong assumption. I don't know why I did. But let's just forget everything we said. We are dealing with supersonic flow. I just wanted to make it a little more interesting and get your guys to jump in. But I think I created more confusion. But that's all right. Let's just forget everything. Let's start from the beginning. Let's say you are coming in with a supersonic flow, right? And you know that your length is larger than L star, right? And you also know that your exit conditions is going to be the sonic conditions because of the adjustments that are going to be made inside the duct. And we also know that there will be a normal shock wave inside the duct, right? So what do we guess? We already know that we have to guess something. We guess a value for the Mach number upstream that shock wave, right? We don't know where that shock wave happened. We say it will happen at an X length, right? We don't know what the length is, right? Okay. So the value that you're guessing is not this length, it's actually the upstream Mach number, right? And we have the normal shock relationships, right? When we have the normal shock relationships, we can get this upstream Mach number that we have guessed and find the downstream properties, right? So we have the properties of the downstream of that shock wave, right? We have the Mach number, we have the pressure, we have the whatever, right? And we know that, so let's just remove this part of the duct. Let's just treat this after downstream of shock wave as an inlet, right? We know that this outlet is always the sonic conditions, right? That's one of the first assumptions, right? So using the relationships we already have, we can find this length, right? This is still a guess length. We don't know if it's a correct length or not, but this is just the length we already have, right? Okay. So the Ly star part, is it clear? Okay. Let's go back to Lx, right? We have already guessed, and let's say your duct is from here to here, right? So we have cut the duct in not in half, but in two different ducts, right? Supersonic condition, Mach 2 coming in, supersonic condition going out, right? Let me actually separate these ducts. So essentially we are cutting the duct, right? Supersonic condition inlet, supersonic condition outlet. So what does this mean? It means that this Lx is smaller than any Ls star you can have because we are not reaching the choking conditions, right? So this is a case of the first case we discussed, right? Where your L is smaller than L star. So this Lx is smaller than S star. And we already know how to calculate that length, right? We actually have to go use the equations. Instead of finding the exit Mach number, you have to find an L, right? Based on the relationships we already have. Is this clear? Yes? Okay, so based on these two, we can calculate an Lx and Ly. Right? We have two L's, right? You can add them up. This should give you the length of the duct, right? If Lx plus Ly star is equal to the length of the duct, this is the same value, it means that your guess for the value of Mach number was correct, right? Does this make sense? Yeah? Everyone? Let me hear it from everyone. Nila?
No, yeah.
Tyler and Victoria, okay. And if it was, okay, what if this Lxy plus Ly star was not equal your dot length? What should we do?
Go back and change your Mach number.
Okay, so should we increase the Mach number or decrease it though?
It's greater than or less than.
Exactly. So if your Lx plus Ly star is larger than your dot length, your L, your original length, then should we decrease the guess Mach number or should we increase it?
Decrease. If it's larger, if you add them up and it's larger, you have to decrease one of the lengths.
Yeah, you have to, exactly. We want to decrease one of the lengths, which means that
You want to increase the Mach rate?
you want to increase the guess Mach number.
Yeah, that can move the shock further forward, right?
Does that move the shock further in? We are guessing this Mach number here.
If the shock wave is a greater number, then it's going to be further back from the choke point. And if we want to decrease the length, we have to go a little bit more ahead. So we would need to decrease the Mach number.
I didn't understand your explanation, but you're correct. Your conclusion was correct. If your Lx plus Ly star is larger than L, then you need to decrease that Mach number you have guessed, right? If it is smaller, then you need to increase the Mach number you have guessed. The M of X you have guessed.
Can we do an example problem of this? Because
We will definitely do an example
because
for it.
guessing and that's kind of
It is a little confusing, yeah. For whatever reason, I confuse you guys a little more.
it is confusing. Guessing numbers. I mean,
It is, yeah, it is exactly. It is always confusing.
Guessing.
So what I'm going to do on Monday is to post the lecture with the solved examples, right? If you guys have a specific part of the chapter that you want to see more examples from, send an email to me, right? Tell me that I want to see an example from this part of the lecture, okay? And then the slides are already posted. So let's just talk we can go over this pretty fast. If you have passed the fluid mechanics course or aerodynamics, you have seen the Moody diagram. The Moody diagram helps us calculate the friction coefficient, essentially, for a fully developed pipe flow, right? And you can prove after doing the integration and relating the shear force to the pressure force. You can eventually prove that 4 multiplied by your friction coefficient is equal to this value. And this value here, delta P over rho B squared over 2 multiplied by L over the hydraulic diameter, is called the Darcy friction factor. And that represents F of D, Darcy friction factor. Okay? This is the equation for laminar flow specifically. If you plot that for the laminar flow, you will get this part of the Moody diagram. Essentially, you have the Reynolds number at one side and you have the friction factor at the other side. And that will give you, based on that, let's say your Reynolds number is this, you find the friction factor on this. Do you see this line? Right? This line, I'm talking about this line. Where is the laminar flow line, right? But if you were in the turbulent flow, you will use one of these lines based on the surface roughness. Okay? Are we familiar with this? The Moody diagram? Yes? Okay. And we have a lot of dimensionless parameters that are pretty important to us in our discussions and calculations. Mach number, of course, is the most important parameter, dimensionless parameter in propulsion, in aerodynamics in general, internal or external aerodynamics. Reynolds number is the next one that actually distinguishes between the turbulent and laminar flow. We have the Prandtl number if you are dealing with the heat transfer. How many people have not passed heat transfer? I know I've checked it a million times. You have not. What about you two? You two have passed heat transfer?
Class.
You are in the class right now.
No, heat transfer, I haven't taken that class.
You haven't?
No, I haven't.
Okay. So you guys are not familiar with the Prandtl number. But that's all right. If we were to use the Prandtl number, I will try to explain it a little more. Also the Nusselt number. You are not familiar with the Nusselt number and the Stanton number. But you are familiar with the pressure coefficient. Pressure coefficient is delta P over rho V squared over 2. In general, any force coefficient is that force divided by the dynamic pressure multiplied by area. Right? Rho V squared over 2 multiplied by area. So that's the general force coefficient. Right? If you're dealing with pressure force coefficient, then that you have the pressure coefficient. Right? We have the Knudsen number that is actually an important parameter if you're dealing with the reactions that are happening inside the combustion chamber, right? Because this number tells you whether you can assume the continuum conditions for your flow or not. And that means that whether you can use the Navier-Stokes, Bernoulli's, whatever, all of those things, all of the things you have learned so far for the analysis or not, right? Does that make sense? And we can rewrite the pressure coefficient as this. We can actually relate it to the Mach number. And if we are in the incompressible flow region, which is where you have only 5% density variation between the total density and the static density, right? Then we can rewrite the equation and find the relationships. We can use the Bernoulli's equation and find simpler relationships for the pressure ratios. Okay, and you can see we cannot use these relationships for the compressible cases because the density ratio is going to become so high. Okay, and the fluid impulse. We have already talked about the fluid impulse, how to calculate the fluid impulse. But essentially, the forces that are acting on the flow, the valve forces that are acting on the flow, you can find the forces acting on the flow by the valves using the fluid impulses at the inlet and the outlet. Okay. And you can make a lot of conclusions about the fluid impulse, but those are outside of this scope of this course. And I guess that's it. I just had to go a little faster at the end. But that's it for chapter 2, and that's it for this lecture. Hopefully you guys have